Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We continue with our fourth module, which is the first module on statistical learning theory, and we continue with our discussion on bias, variance, etc. Now, so in last two talks, in first talk we generally discussed about statistical learning and various sources of bias, various sources of error like bias, variance in general terms. In second talk we gave you that conditional distribution framework for bias variance and formally defined it. In third and fourth talk we did some explicit examples where we computed bias variance. The third talk's examples were rather artificial. We admitted, just wanted to explicitly show you what kind of expectations are needed to be calculated. And now finally in last talk we gave you one example which was somewhat real life example, but under heavy linear assumption, like we were trying to model price of a house based on the area of the house, and we assumed that it follows a linear model. Under that assumption we saw that of course linearity will lead to unbiasedness, that is bias will be 0, and we showed that all the variance can be calculated using the explicit values of those linear model parameters, and the fact that we were assuming x takes discrete uniform distribution with 3 possible values. In fact, as long as x is a finite distribution, because those expressions we saw in last class were functions of x only, as long as x were finite and with known probabilities, those expressions can be calculated using some computer program. So that calculation was possible. Today we continue our discussion with this. So just to recall, we have just a setup. If you have two sets of random vectors which were being jointly distributed, either having a probability mass function where you can compute the probabilities of specific values, and probability of a set will be sum of the probabilities of these values, or you have a density function such that for probability of a particular set will be integral of that density function over that set. So this is the situation, just to recall, where probability of xy belonging to probability of xy belonging to A will be summation of the probability x equal to A comma y equal to B, where for all A comma B in A. This is the probability mass function situation, where probabilities you can assign point probabilities to all points, and probability of every set will be just sums of those probabilities. This is the scenario. So this is the mass scenario, but this is the scenario. The density is slightly different situation, where probability of xy belonging to, I'm sorry, something is going on in my head perhaps. Probability of this is integral over A of this function over this set. Now this is, as we discussed, allows you to tackle the situation where probability of a point is 0, probability of all point is 0, but nevertheless there are sets with non-zero probability. So the probability of a set is not necessarily sums of the probabilities of all points, because sums of the probabilities of all point will, let's say, be 0 for each point. Every point that's possible, that probability of that point is 0, but nevertheless one can have non-zero probability for non-point sets. So for example, if you choose uniformly a point between 0 to 1, probability of that point being equal to any point will be 0, but probability of that point being between 0 to half will be half, or between 0.4 to 0.9 will be half. So probability will be decided by the area, or the length of stock area, in this case the length of that interval, and in case of uniform distribution in 2 dimension, let's say 2 dimensional space B. So suppose you have a space B, so if xy jointly uniform B will imply probability of any A, sits inside is just area A divided by area B. This is what one will get. Now, this is what we used heavily in last class. I am recalling it once more, the law of iterated expectation. So, if you have two random variables, like random vectors x and y, if you want to take the expected value of xy, unconditional expected value of xy, you first find the conditional expected value of gxy with respect to the conditional distribution of y given x, and then take the unconditional expectation of this function expected value of y given x gxy. Because in the right hand side, the one inside the bracket becomes a function of x only, because when you are taking expected value of gxy with respect to the conditional distribution of y given x, you are keeping x fixed and taking the average over the distribution of y given x. So, for every value of x, you get a value for that thing inside the bracket. Now, that is a function of x, so you take the average of that function now with respect to the distribution of x. That actually law of conditional iterated expectation tells you, that gives you unconditional expectation of this function. This is quite important, as we saw in statistical learning theory. So, same setup, you are drawing a sample and trying to model y in terms of x. You have an algorithm, you feed the data, the sample inside the algorithm comes up with a rule. The rule depends on the particular specific sample you are entering there. So, because the sample itself can be random, Hs itself becomes a random variable. You want to study the behavior of Hx, you want to study how good predictor of y Hsx is for various s, and in fact, you want to also see how good predictor of y Hsx is for every x. And so, you want to know how good prediction for y Hsx is for fixing x and varying s, fixing s, varying x, and varying both of them together. Various aspects of this behavior leads to various components of potential errors in this prediction. So, we saw one aspect of this error will be bias. The bias is you take the average prediction for, so fix a value of x, fix a value for x, call it small x, take all the predictions Hsx, vary it over all possible samples, and then take the average value with respect, average it over all possible sample, call it h bar x. Take y bar x, which is the conditional expectation of y given x, that is an average value of y when the value of x is small x. Take the square difference between these two. This square difference you find for every value for x, take the average over all x. This is the bias. So, I think I drew this picture, just let me draw it again. Suppose this is your distribution for various x's, these are the, so for various x, these are the actual expected values of y. This is expected value of y given x1, this is x1, expected value of y given x2, and so on. This is x2, here this is x2, this is x1, and suppose these are your predictions, various predictions. Now, on this line, let us say this becomes the average of these three. On this line, or let us say this becomes the average of these three. On this line, this becomes the average. On this line, this becomes the average. So, these are h bar x1, this is h bar x2, this is h bar x3. Take the squared distance, not explicit distance, but the squared distance of these. Now, once you have these squared distances, note that you will get for each x line, you will get a squared distance. Take the average of them. That gives you this bias. This bias essentially for this picture gives you this. So, suppose the correct values actually correct average values for x and y. For every x you are taking the actual expected value of y. Now, you move x's, suppose they move on this line, and suppose somehow your models are somewhat below. If you take the averages of these models, if your models are in a way, your algorithm is bound to remain lower than the actual, that will be reflected in this difference between these averages. This is what is called bias. So, this is something inherent to the algorithm. Algorithm is such that it is predicting values lower than the actual value. Suppose that is the algorithm, then that is what the picture will be. I mean, an algorithm can be algorithm can introduce many such intricacies. That is what I was saying. After all, algorithm intends to find a rule that defines y in terms of x. Algorithm by definition is a finite possible thing. It can only search amongst finite possible rules. So, it searches amongst finite possible rules. Suppose that finite set it targets itself has certain constraints which does not describe, which does not fit with the model. Now, a priori you have no idea to, when you are fixing the algorithm, a priori you do not have any idea what the model is. You just somehow have to put some constraint. Let us say, if you can somehow the data follows a 100-degree polynomial. The x and y relation follows 100-degree polynomial. Now, if the data you are getting, suppose it is of a size 10. From a size 10 data, there is no way you can guess that it is a 100-degree polynomial. Now, once you get the sample, you have to get into the business of modeling. You receive the first sample. Before you start modeling the algorithm, maybe you can tune the algorithm a bit and then apply that algorithm on that model or on that data and come up with a model. Just by looking at the data, visualizing the data, you can get some thoughts, like maybe this is coming from this kind of distribution, but that is not foolproof, because clearly a 100-degree polynomial relation will not be reflected in a size 10 or size 20 or size 30 data. So, when you are starting, when you are running the algorithm first time, you have to have the algorithm ready before you run the first time, right? And then for that particular algorithm, you decide how good that algorithm is, how nice it is predicting the results, etc. You can see the data before tuning algorithm, but then you have to do it. So, once you have started working on with the given data, you have already put a constraint on the algorithm. So, it is searching on a finite search space. Suppose that search space itself has certain constraints. So, for example, by looking at a degree 30 size data, you have thought maybe a degree 7 polynomial will fit it. Actual thing is degree 100 polynomial. Clearly, this guess has put a constraint on your search, that your guess that maybe a degree 7 polynomial will fit it well has already put a constraint on your performance, on the performance of your algorithm, because your data is coming from a degree 100 curve. And of course, algorithms have limitation. So, maximizing or fitting a degree 100 or degree 1000 curve will have cost, it will have cost, it will be more costly than fitting a low degree polynomial. And secondly, there is another problem. If you have a degree 30 size data and you start with trying to fit a, let us say, 50-degree polynomial, it will perfectly fit your data. For general data, general distribution, it will clearly create an overfit. So, these kind of constraints are already there when you are building an algorithm, and hence you have to start with certain constraints. So, and that constraints will almost certainly will be reflected in your model, and this inherent difference between the model and your algorithm is the bias. And second thing was the variance, where how much the algorithm is sensitive to your particular data. If the data set changes, how drastically the algorithm changes. Now, for a particular data algorithm as a target search space, finite search space, for a particular data, it hits one element, one model in that search space. For the whole data set, for the all possible samples, let's say it hits a subset of this search space. That subspace, the models that are achievable via that algorithm for various samples, the spread of that subset is the variance. That means, in simple terms, if you vary data sets, the models you get, how much they differ from each other. And this is, you take all possible models and take their average. That's your average prediction of your, that's the average of all your predictions of y in terms of x, and then take actual average of y with respect to x, that is the conditional expectation of y with respect to x. Take the squared difference between these two for all x, that's a function of x. Take its average when you vary the x's, that's the bias. Now, let us do some more examples. Suppose your population data is the following. Your actually the relation between x and y is like the previous house price situation, is fairly nicely modelable by a linear model, namely y equal to some x plus epsilon, no slope, no intercept. Just let us say the y equal to x curve moderately describes the population. Your x is a random variable which is varies uniformly between 0 to 40. This epsilon you further somehow you have this assumption that epsilon has expected value of epsilon 0 and epsilon has a constant finite variance sigma square. So, in particular, x varies from 0 to 40, and for each value of x, y varies in these regions. Suppose you have such a population. So, this is your population. You want to model this population based on some algorithm. Let us say you want to model this population based on some algorithm. What will be a very nice prediction? What will be a nice prediction? Least square estimate. If you draw a sample from this population, first of all, if sigma square is small, the points will be always between this and this will be a very thin strip. Whenever you fit a line, this will be very similar to y equal to x. Now, if sigma square is small, you vary different sets of points, these lines will not be very different from each other. First of all, least square estimate for a linear model, bias is 0, that is what we saw. The bias will anyway be small. In fact, this is also kind of clear from this picture. If you have this thin strip, you take a line, the average over all lines for any x will be somewhere in that. For you fix an x here and fit all the lines that will kind of pass through these points chosen from this blue strip, there will always be this kind of things. Average will always be on this line. Because this variance is, if you choose this variance to be small for any size of sample, because this is inside this will be dominated by sigma square anyway, this spread. If this spread is small, the variance will be small. And as far as bias is concerned, conditional expectation of x will be on this line, conditional expectation of y given x will be on this line. It will be actually conditional expectation of y given x is x. So, this is somewhere here. If this spread is small, the average of these things will also be on this line. So, the difference between them will be small. If sigma square is small, both bias and variance will be small because this everything will vary within this thin strip. Now, let us see what happens for general sigma square. If it is general sigma square, you are doing least square fit. For least square fit, for a linear model population where the population has a linear model, for least square fit it's still unbiased. So if you take bunch of points and find the estimator which minimizes the square difference between predicted and actual in terms of a linear function, then we discuss that Gauss-Markov theorem will say this is an unbiased estimator. It will still be an unbiased estimator, so the bias will still be 0 whatever this sigma is. What happens to variance? So for sample size n, for linear model, because this is a linear relation already, variance will be of the order sigma square over n. As n goes to infinity, variance will go to 0 for all sigma square. You don't need to assume sigma square is, variance will go to 0 for all sigma square. You don't need to assume the sigma square is even small if you are, as long as you are taking a large sample. So let's see, let's discuss this. This is an example of a model where both the components of nuisance, bias and variance for the modeling are less. So let's get into this. So this is, we are taking a sample consisting of 5,000 points, which is already pretty big. You are drawing this least square line, so you are just basically minimizing the squared error. You are taking this linear model, you are taking the minimizing the squared error on this. This will give you least square regression line, and for the least square line you will get things which will be very close to fx equal to x. Oops. So bias of the least square line is actually same as the bias of the unconditional or the conditional expectation of this. So expected value of least square fit HS equal to actual linear model of the population. That is, in this model where y equal to x plus epsilon, expected value of, so epsilon follows normal 0 sigma square, or doesn't even need normal, expected value of epsilon is 0, variance of epsilon sigma square, expected value of y given x is x. This is what your y bar, expected value of y given x, and h1, if h1 is least square fit, then expected value of, so then h1 equal to, say, h1, or rather h1 is your least square fit x plus bx bs least square for s, then expected value of a hat actually is known to be 1, expected value of b hat is known to be 0. So this follows from Gauss-Markov theorem that we discussed last time, just mentioned it, and we will get into it when we do linear regression in full details. So this tells you the bias of this estimator will be 0. This is an estimator which has 0 bias. Now let's go to the variance. the variance will be the difference between average and the fit. So, the expected value, so the H1 was, so H1 is the expected value of H1 bar will be your expected value with respect to S of H1x. But these are least squares. So, you have AS, BS. All these are of the order sigma square over n. So, this will involve AS, BS. So, it will involve variance of AS, variance of BS, so with respect to S, and covariance of AS/BS. All these things are of order sigma square of n for least square. It's pretty much clear from the picture, but like this description of these properties of least square will make it even more clear that these are all of the order sigma square over n, and hence as n goes to infinity the variance goes to 0. So, if you take large sample, the least square fit for a linear model where the background is known to be linear is actually and low bias low variance model. But remember, this is really hyper idealistic situation, because you are kind of assuming where your model is your population follows a linear relation and you are choosing a model which is also linear. So, you are basically guessing the population pattern bang on target. Not only that, you are assuming that sample size is also big. Well, if for small sample, in general, if your n is small, the variance will be of the order sigma square over n. So, in general it is sigma square over n. These values are of the order sigma square over n, what we discussed last time or in last few slides, that this is of the order sigma square over n. If n is small, some variance will be there. If n is small, the prediction, the least square line indeed depends on the, least square line fit depends on the sample point. So, for example, if n is 2, then sigma square will lurk. So, this picture, this your model was looking like this. This amount of variance will be there, because if your model is, let us say you are doing with 2 points, this curve will go through this and this curve will go through this. So, this much difference will be there in the possibility of all possible fits, but the point is, if you take too many lines on an average, this will be very close to the actual line y equal to x. So, that is the idea. So, not only you are guessing the model correctly, the type of the relation correctly, that it is a linear relation and you are guessing it correctly, you are also taking a large amount of sample points, a sample of large size. So, this is an example of a low bias low variance model. The next one is high bias low variance model. Do the exactly same thing, fit the least square curve, just hack it up by 100. The model is same, y equal to x plus epsilon, just add 100 height 100. Now, of course, adding extra spread does not change the variability, because it is just here the whatever the variance was there, it will be the same thing here. So, variance will still remain sigma square over n. So, if you take large size n, if n large, this is definitely low variance. Variance of H2, just from the picture it is clear, same as variance of H1. We prove it in details here, but it is clear from the picture. But average value of H1, so average of H2 just by this picture has to be equal to average of H1 plus 100. So, this will contribute to bias. So this is an example of a model which is high bias, low variance. Done the calculations in details using all the conditional expectations, etc. It's again, H1 is again the least square part and H2 is just H1 plus just one, constant term 100. In this picture, this red line is your H1, the previous prediction, and the green line is H2. The picture itself shows that if this is your actual population and this is the model, this clearly there is a difference between center of the model as center of the predicted model versus the center of the actual population. So this is where you can see that the expectation of course will get shifted by 100 and this will get reflected in the bias. It's a squared thing, so the bias will be 10,000, but the variance of course doesn't depend on shift, so variance will remain the same. So this is an example of a high bias, low variance model. Now, what about the high bias, high variance model? Here is an example for the same population and high bias, high variance model. You both shift it and add an extra dimension of variability. How do you do that? This is again, of course, why do you want a high bias, high variance model? Because this is just a terrible model, I know. So you don't want a terrible model, but just for the theoretical interest, I am just showing you what potentially will be a high bias, high variance model. So you first of all assume n is greater than equal to 3, let's say, otherwise this will not work. N has to be greater than equal to 3. So now fit a least square model using x2 to xn. Fit least square line from x2 to xn, and this is, assume IIT. This is sample is IIT. Okay. Take x2 to xn, a least square model based on x2 to xn. Call that h1. Add 100. Along with that, add this factor x1 minus 20 and multiply x. So this has to be a function of x. So for every x, your model is that you take the least square line and whatever the value that line gives at x for y, add 100 and multiply x with x1 minus 20 and add it to the mix. What does it do? The x, x1, x has same distribution as x. So x1 follows uniform 0 to 40. So x1 minus 20 follows uniform minus 20, 20. So expected value of x1 minus 20 is 0. So when you take the expected value, this term does not contribute. So when you are taking expected values over all models, when you are varying x1 over all possible, when you are varying over all possible s's, this becomes essentially all possible, potentially taking all possible x1 minus 0 and their average. That average will be 0, no contribution from here. The expected value of this is least square estimate. So expected value of this is actually x. So expected value of h1s x is x. This is because least square, this is the least square fit, and expected value of this is 100. So this portion keeps it near the actual model. This portion does not contribute to the expected value 0. This portion hacks it up to 100. But what does this portion do? This portion hacks up the variance. Why? First of all, the shift by 100 will not contribute to the variance. So, shifting by 100 does not create any problem in terms of variance, whether it is here or here does not matter, shift do not contribute to variance. Whatever for the various models, they are only incorporated in here. So, the variance of this portion will contribute to the variance, this no role in variance. What it does, it ruins the unbiasedness of the model, introduces a permanent biasness by shifting the center from the actual center. What does this, the other portion do? They do not contribute to variance. Now, there is a reason I did it with x2 to xn, because x1 y1, this is an IID sample, x1 y1 independent of x2 y2 up to xn yn. So, when you are taking a variance, there is no covariance between these two, no covariance term. Hence, variance will come from variance of h1 plus variance of x1 minus 20 times x. This is low, we saw, but this is going to be high. Why? Well, x1 minus 20 itself is uniform minus 20 to 20. This is high variance. This itself varies in a length 40 strip, so that has a fairly high variance. So, this is what gives you a high variance, high bias model. And this already shows you how to get a high variance, low bias model. So, if you take, this is H3S, this is high variance plus high bias. If you take H4S, which is just H1S plus x1 minus 20x, everything else I said will remain intact, except this shift will not be there, shift by 100 will not be there. So, this will be low bias, high variance. So, the formal calculations of these are there. You can slowly see the expected value calculations, which we did by taking conditional expectations, etc. This is least square fit. So, the expected value of this actually gives you the conditional expectation of y perfectly. Expected value of this is 100, expected value of this is 0. So, expected value of this thing is this whole thing, expected value of this whole thing is actually 100, which already introduces the bias. So, then it's 100, so it gets squared, so the bias will be 10,000, just like the second model. As far as variance is concerned, this is the variance calculation. Once you take care of the covariance term, because x minus 20 is coming from the first data point in the sample, and these things are coming from the second to nth data point, it's an IID sample. So, they split out, it's just the expectation of this. Now, you take the expectation of this as fixing x, that gives you, x comes out, and you take the variance of this. So, this essentially becomes variance of x minus 20 times expected value of x square. This is just this is 40 square over 3, and this value is also pretty high. So, this comes out to be, this is 133 times 40 square over 3. So, the variance of this is 133, because it's a uniform minus 20, 20. So, uniform over a spread 40 interval. So, that gives you a fairly high variance. And similarly, you can do the calculation for the other one, that's also gives you the same amount of variance as we discussed, just no bias is there. So this is how you get the low bias high variance model, by simply not taking the 100 shift and doing the rest for as in the last one. Thank you. This just give this talk just was playing with various examples with low bias, low variance, high bias, high variance, low bias, high variance, high bias, low variance. So this demonstrates basically how those things can be achieved, and hopefully this gives you an idea about the nature of these two nuisances in model bias and variance. Thank you. Let me stop here.